Hi everybody, welcome to Climate Change Calculated Part 1. So first I would like to introduce myself. I'm Gerald Schuller, Professor in Media Technology at Ilmenau University of Technology in Germany, and I'm Head of the Department for Applied Media Systems. And here I will present a series of videos that deal with calculating climate change, possible solutions to the shown results, pointing out media technological approaches and techniques, and also to give ideas for own calculations. So climate change is everywhere in the news, and media technologies such as the internet and social media easily lead to confusion and misinformation. But the internet can also be used to check information, and this is essential in times of unfiltered mass information. And this will be shown below. So first to numbers and calculations. These are important for checking claims. Right? Numbers are verifiable, they are an important part of reproducible research, and they are also comparable. And references are important for verifiability. So if there's a claim, there should be a reference where this claim can be checked. And the internet offers new opportunities with open data to calculate things and for checking. Often rough estimates of magnitudes are sufficient, focusing on the main effects to check for plausibility. An order of magnitude means that the decimal point is in the right place, which means an accuracy better than a factor of 10, but perhaps even better. So what are our tools? These are mathematics, physics, usually high school physics is sufficient, then engineering, then I'm using the programming language Python under Linux, but usually a normal scientific calculator does it too. Then in general, methods and tools of media technology, and of course open data, which in our context means data which is openly available on the internet. So then let me start with a problem description. First we can take a look at data from NASA. So we can take a look at this link. Let's see if it opens. So here we can see this link, and right in the beginning you see this nice chart of the CO2 concentration over time. And here you can see the CO2 concentration in parts per million, and here's the time axis. So 0 is present time, and then we go back in time, back to 800,000 years before present time. And you can see here that the CO2 level is fluctuating between about 200 ppm and about 280 ppm. So it turns out that this lower fluctuation here, this lower end, about 200 ppm, happens when there is an ice age. And this upper end here happens when there is a warm age. So currently you can see this is the last ice age, here down here, and then we are into this warm age, so currently we're here. But since about 1950 we have this kind of explosion of the CO2 concentration. You can see here it goes from 280 above 300, and currently we are over 400 ppm. So this is actually even more than the fluctuation between ice age and warm times. So this shows something unusual is going on. The question is, what is the cause of this sudden jump in the CO2 concentration? So let's go back to the slides. So this is from NASA, but just for checking, for comparison, we can also take a look at other measuring stations, for instance in Germany, here in the state of Thuringia. So we can just open this link here. It shows us the measurements of some local stations. If we can scroll down here. So here we can see local measurements. Not as far back, but the most interesting time here, this is the year 2000, and then it goes up to 2015. And here you have the same measurements basically. So here the orange is the measurements that we just saw from the NASA website, and in blue you can see a mountain in Thuringia, and in green you see the measurements from the city of Jena. And you can see it's actually even higher than the one from Mauna Loa on Hawaii. And this is also why the station is used. It's close to the equator. Hawaii is close to the equator and also far from industrialized areas, which cause more CO2. So this actually gives the cleanest estimate here. So going back to the slides. So you can see this local station basically gives us the same measurements basically. So to analyze it more closely, we can also download these data from the internet as a so-called comma-separated variable file, which we can then use in Python. We can read it in Python and then use it as basis for our own calculations and plots. So here this link actually allows us to download this data down to year 1. So 2000 years ago. So here's the result. So I wrote this little Python script called co2plot.py, which is also in the link to this video, so that you can download it yourself together with this CSV file. And then I plot this data, and this gives us the more recent data. So here you can now see starting at year 0, and this is present, so 2019. So you can see basically the same trend. Here around 1800 is the start of the industrialization, and then here we have basically, which looks like an exponential rise. So here the steep rise in the present. You can also plot the data more closely for the industrialized age from 1750 to today. And this is the plot that we get. And we see approximately in 1910 we have exceeded 300 ppm CO2 concentration in the atmosphere. And in 1944, so 34 years later, we exceeded the 310 ppm mark, so not that much increase. But then in 2016 we already hit the 400 ppm mark, so this shows the steep increase. So here you can see the curve. So here 1900 we have a marked, a clearly visible increase. Then 1950 starts where it really increases. And now we are at over 400. So you can also plot the ice ages on top of the CO2 plot. And this is a picture that you can actually see here in this link. And this is what you see. So here down here, the blue ones are the ice ages, and this plot here is the CO2 concentration. And here we can see that each time there's an ice age, there's also a low concentration of CO2. Each time we have a warm age, we have a high concentration of CO2. So there's a quite nice fit between the two curves. So during ice ages, we observe about 200 ppm by volume CO2, but in warm periods, approximately 280. So this was also true until about the beginning of the industrialization, 750, 1900. So our observation is that over millions of years we have this equilibrium, right, between warm ages, ice ages, and 200 ppm, 280 ppm. Basically, we have CO2 production by living things like air decaying plants and volcanoes, and then we have CO2 decomposition or absorption by plants, and also weathering of mountains. They absorb CO2. And then we see these approximately 100,000 year oscillations of the CO2 between ice ages and warm times. And they are said to come from the corresponding oscillations of the Earth orbit and by ocean currents, which sometimes bring more or less seaweeds, such as algae, to the surface, which absorb more or less CO2 accordingly. So it can be read here. So that's kind of a natural cycle, this up and down. So the problem that we see during ice ages, the glacial periods, the CO2 concentration is about 200 ppm of CO2, and during warm periods we have about 280 ppm. But then, since about 1950, we observe this sharp increase in CO2. At the moment, this CO2 concentration is about 410 ppm, or even more, which is about 50% higher than the historical value for warm times. And it's already bigger than the difference between cold and warm times. Very unusual. So, also, the increase that we observe is almost like a jump. This increase is faster than ever before. It's what we can see in the plot, like the past 800,000 years, there's no increase which is as steep as we observe today. And even if you look at charts which go further back, there was never such a fast increase. So the question is, what does the modern day CO2 increase mean? What is the cause and what are the consequences? So first, let's take a look at the definition of parts per million. Right? Parts per million stands for 10 to the minus 6. Right? So 1/1,000,000th, basically. So for comparison, per mil stands for thousands, or 10 to the minus 3. Therefore, we can convert 400 parts per million is 400 times 10 to the minus 6 is 0.4 times 10 to the minus 3, or 0.4 per mil. So this actually does not sound very much, but if you think of it as a blood alcohol level, you can see that it can still be significant. For instance, this level would be enough for an inability to drive a car. Right? So just because it sounds not much, it doesn't mean that it doesn't have an effect. So this ratio of ppm refers to the volume, usually for gases such as CO2, or mass, for instance for liquids. So the question is, what has changed in modern times? Right? This sudden increase that we observe since about 1900. So for many millennia, humanity has used the burning of wood as the main energy source. And the released CO2 from this burning was extracted from the atmosphere only decades earlier by the growth of the trees. So it basically was a zero-sum game. But since industrialization, and especially since the 1950s, through mass production and mass mobility, coal and oil has been the main source of energy, fossil fuels. Right? So the released CO2 was withdrawn from the atmosphere in the age of Carboniferous. So you can read about it. This is the German Wikipedia page, this is the English Wikipedia page. And this age is about 300 million years ago. So it's really ancient. And this is an age which lasted about 60 million years. So a long time. So from that age came the plants that have formed coal and oil over these millennia. And that's even before the age of the dinosaurs. So in effect, what we do with the burning of coal and oil is similar to the film Jurassic Park, where dinosaurs were brought back to life. Only that now we bring CO2 from even before that area back to life, or rather back into our atmosphere. So what we burn now has been removed from the atmosphere over a period of some 60 million years. And now we are releasing it within only a few centuries into the present. Right? And that's why we have this steep increase. Basically, we bring back the atmosphere from 300 million years ago, all of a sudden in the present. So, the question is still, is human activity sufficient to explain the CO2 increase? Or is it maybe volcanoes or whatever? So we can actually answer this question by calculating, by calculation and use of open data. For this calculation, I use floating point numbers and this notation. 2000 is 2 times 10 to the 3 or 2e3. So 2e3 is common notation for scientific calculators and also programming languages like Python. So we can find actually the total fossil CO2 emissions from the entire world since 1960. So we can take a look at this website here. So we can click on it, open it, and here we can find this nice plot. I can make it a little bigger. So here you can see the year 1960, here we have the year 2017, and here we have the total CO2 emissions in million tons. Right? So here we have 5,000, here we have 10,000 million tons, and 1,000 million is also a billion, and a billion is also abbreviated as giga, so we have 10 gigatons here. So this is 10 gigatons in 1960, and in the present we have over 35 gigatons. And it's also interesting to look at this recent trend. So actually here we have some flattening of the emissions. So it's kind of looking like saturating around 2012. Looks like saturating, but then around 2017 here we have an uptick again. 2016 it increased again, 2017 it also increased again. So it's kind of interesting to observe, because this area is where the Paris Climate Accord was agreed to, and this was the era of Obama, which was really after climate change. And then 2016 Donald Trump came into power, and he's abandoning the Paris Accord, and it seems it looks like it's having some influence, many countries then don't take it seriously anymore. So here this uptick. So that's my speculation. I don't really know. So going back to my slides. Yeah, so we can even find data since 1750 here in this link. And we actually use this data in our analysis, which we now do. So again, we use comma-separated variable data representations. So we download this data from 1750 and again read it in a Python program. And this program plots the two data sets starting 1960 and starting 1750 on top of each other to basically find the sum, the total amount of CO2 emitted into our atmosphere since 1750. Basically, we just need to add up each year to find the total sum. And then this total sum gives us the theoretical concentration increase in our atmosphere caused by humanity by burning fossil fuels. And this sum, from our program comes to 1580 gigatons. So giga again is 10 to the 9th. So we can let our program run with Python 3 CO2 global twin plot.py, and then we get the total emissions. Which you can see here basically. This is the plot that it makes. So here you can see green is the data since 1750, then blue is the data from 1960. So you can see they are almost identical, except here there's a few differences. And this is also interesting because this shows us the accuracy of the data. Right? The amount of difference that we see here is the boundary of accuracy that we have for those measurements. And we see this is actually pretty good. This looks like within a few percent. And then to test my guess that we have an exponential increase, I also let this program fit an exponential curve, which is in orange here. And you can see it's actually quite a nice fit, except here in the end. So here we have some flattening, which gives us some hope that it's possible to escape this exponential growth. So this actually can give us some hope. Yeah, and here you can see actually the formula that my program here found. So basically this is the formula which plots this graph for the gigatons. So here X is the year, like 1980 for instance, and then the result of this formula is gigatons. Yeah, so for us most important is here this total sum, 1580 gigatons, which we can now convert to a concentration. Yeah, so to see the concentration we need to set it in relation to the mass of the entire Earth atmosphere. Right? And again, we can use open data to find the total mass of Earth's atmosphere. So here we have two links. Both give us the total mass, and we can find the total mass is 5.15 times 10 to the 6 gigatons. So a lot. Right? So now we just need to set it in relation. So the concentration of the CO2 emitted by humanity since industrialization therefore would be the CO2 mass divided by the atmospheric mass, or in Python 1580 gigatons divided by 5.16 times 10 to the 6 gigatons, and the result is 306 ppm, but for mass. But since we have gases here, for gases the ppm is usually used for volume. So now we have to compare the volume of CO2 to the volume of air. And again we can find the volume of carbon dioxide, CO2, in the internet, in Wikipedia. And we find CO2 has a density about 1.6 times higher than air, which means it takes up less volume. And therefore we have to divide by this factor for this conversion. So we need 306 ppm divided by 1.6, and we get 191 ppm by volume. So this is basically the concentration increase that we would expect from human activity. So adding this concentration to the pre-industrial level, starting with the industrialization of 208 ppm, gives us 470 ppm. But now we compare it to the current level of about 410 ppm, we see that this is actually 60 ppm more than what we observe. right? And that means human activity is therefore for more than 100% responsible for the observed increase. So this is a surprisingly clear answer, right? More than 100% responsible. So the additional amount of 60 ppm could have been absorbed by nature, for instance, oceans, leading to them becoming more acidic, and forests, as part of a slow control loop of nature. Nature tries to absorb those additional CO2, but it can only do so much. So here we find nature can only absorb about 60 ppm since industrialization. So that's actually not that much. So suppose that this control loop of nature has been active since the significant increase of CO2 from 1950. So for about 70 years, right? Then we have an annual CO2 reduction of 60 ppm divided by 70 years, which is 0.85 ppm per year, right? So we can convert this back to mass of CO2. So we take ppm in volume times 1.6 times Earth's atmosphere mass, and then we get 7 gigatons. So basically nature is able to absorb 7 gigatons of CO2. So this is basically a lot, but much less than what humanity puts in, right? And we actually see in our Python plot that this amount that nature is able to absorb is roughly the output of 1950. So 1950 we were kind of in an equilibrium, but since then we left it. So with this value of 1950 we would have no further increase in CO2 concentration because nature can absorb it. So here you can actually see it again. Here's 1950, and here we have roughly our 7 gigatons. Right? So this is where we actually should be. Yeah, so assume we want to really reduce the CO2 emission, and assume we theoretically would go down to 0. Right, then we can calculate how long it would take to go back to the pre-industrial level of 208 ppm. So let's assume that we have a linear degradation with a fixed degradation value of 0.85 ppm per year. Right? It's actually not really realistic, but it's easy to compute. So then we can compute the degradation time, which is necessary to go back to the pre-industrial level, which is 410, the current level, minus 280, divided by 0.85 ppm per year, and this comes up to about 150 years. So it would take about 150 years to go back if we suddenly would stop burning fossil fuel altogether. But this assumes that we have this linear degradation, but usually an exponential decay with a fixed percentage every year is more likely to be realistic and accurate. So again, for comparison, I found this link here, which says between 65% and 80% of CO2 released into the air dissolves into the ocean over a period of 20 to 200 years. So that actually fits the order of magnitude that we computed pretty well. But then the rest is removed by slower processes that take up to several hundreds of thousands of years, including chemical weathering and rock formation. So that's a long time, several hundred thousand years. So, but at least our rough estimate has a good match again. So in conclusion, for the CO2 concentration to not further increase, we would have to reduce the annual fossil CO2 emissions to the value of approximately 7 gigatons, which is the value of 1950. But our plot also shows at the moment we are at about 35 gigatons, about 5 times that value. And that means we need a reduction of 80% just to get back to 1950 value. And this would be just sufficient to keep the atmospheric CO2 concentration from increasing any further. So it's not even enough to reduce the level. If you want to reduce the concentration, we need to reduce our CO2 emissions even further, more than 80%. So that means saving energy is no longer enough for the reduction by 80%. Saving energy maybe gets us to 20–30%, but that's by far not enough. So we need to do much more. So we should barely burn any fossil fuels. So basically we need to keep oil and coal in the ground and don't burn it at all. So instead we need to switch completely to renewable energies, right? That can be wind, solar, or something that grows. So it's not enough to just change the biggest emitters. We all have to join, all countries, big and small, and all sectors, whether transport or industry or households, because we need to reduce so much. In order to preserve or strengthen nature's ability to decompose CO2, which is the 8.85 ppm per year, we must also protect oceans and reforest forests so that they're able to continue to absorb this level. At the moment we do the opposite, right? We deforest the forest and also the oceans getting more acidic, which means there's less life and less absorption of CO2. So this is also crucial, to have nature absorb CO2. Yeah, so that leads me to my next video. In the next video, we answer the question, does the CO2 concentration actually increase the global temperature or influence the global temperature? Okay, then thank you for your attention, and until the next time, goodbye.